Now, other set definitions. Countable set. Countable set is defined as uh, a set whose elements uh, has one-to-one correspondence with the natural numbers 1, 2, 3, 4, 5. So you can count the elements inside a countable set. The opposite is called uncountable set, which cannot be you cannot count. Empty set is also called null set, and you use the symbol phi, which is a set without any elements. By the way, W/O is defined as a without. So it's nothing. Uh, and finite set is a set of either countable or the empty set. So with a finite number of elements. So that means uh, the number of elements inside a set is uh, not infinite. And the opposite concept is called infinite set, of course. And for example, you have a countably infinite set, which is, for example, you have a natural number, capital N. Capital N is greater than 0, and they are all integers, 1, 2, 3, 4, 5, etc. So this is the set of all natural numbers. It's a nice example of a countably infinite set. Some of you guys have already noticed that the set concept is equivalent to the event defined by probability function P, uh, uh, which I will discuss later in detail. A subset A or B, that means A is contained in B. So the set A is contained or included in the set B. So I use the symbol A included in B with the underbar over there in the symbol. A proper subset A or B is a little bit different. There you just at least one element in B, not in A. So I will use the symbol A included in B properly. So it looks like this. And we have a very important concept, mutually exclusive sets or disjoint sets. It means there are absolutely no common element between A and B. So the set A and the set B, there are no common elements. That means A intersection B is the empty set phi. Something like this. A and B are separated. And a universal set S is the largest or all-encompassing set of elements. So that means this is the total set defined in the system. So we have an example, A, B, C, D, E, F sets. Okay, so the set A, 1, 3, 5, 7 as elements. This is in a tabular method, and the set A is countably finite. The set B is whose elements are infinite, 1, 2, 3, 4, 5, etc. This is in a tabular method, and the set B is countably infinite. Set C, the element small c is greater than 0.5 and less than or equal to 8.5. This is in a rule method, and set C is uncountably infinite. Set D, it has only one element, 0. This is in a tabular form, and D is a countably finite set. Set E, it has 2, 4, 6, 8, 10, 12 as elements. This is in a tabular method, and set E is countably finite also. Set F, the element small f, is between minus 5.0 greater than minus 5.0 and less than equal to 12.0. So this is in the rule method, and f is uncountably infinite set. So as a result, A is included properly in set C, and set F. Sets C and D are included in set F, and the set E is included in set B. Sets A, D, and E are the mutually exclusive sets. They are all separated among A, D, and E. Okay, another example. We have a problem of rolling a die, 주사위 던지기. So our universal set is very simple, defined as S, whose element is 1, 2, 3, 4, 5, 6. Only 6 elements inside. The first condition, a person wins if odd. The second condition, another person wins if less than 5. We have 2 conditions. So let's define those concepts with the sets. Set A is the first one, first condition. So it contains elements 1, 3, 5. Then a person wins because they are all odds. The second condition is set B. Is described by this 1, 2, 3, 4 because they are less than 5. So the total number of the universal set is n. For example, we have 6 of them. So that all the possible subsets, the number of all the possible subsets will be 2 to the power of n. Therefore, if n is 6, then 2 to 6 becomes 64 ways of defining winning with one die. Okay, so you can now the Venn diagram. This is a geometric description of sets. So if we say B is a subset of A, B is included in A properly, and C is mutually exclusive with both set A and set B, then it looks like this. We have a universal set S, B is included in A, and the C is separated from both A and B. And we have equality and the difference definition. Set equality is we say A equals to B. That means necessarily and sufficiently A is included in B and B is included in A together. So we call this equality. And difference, it means A minus B. So A is subtracted by B, which is equal to A intersection B bar. B bar is the complement of B. So you can easily prove by using Venn diagram. For example, if let's say we have A whose element is small a is greater than 0.6 and less than or equal to 1.6, and B is defined by the element small b, which is greater than or equal to 1.0 and less than or equal to 2.5, then A minus B, you have a new element C, which is greater than 0.6 and less than 1.0, and B minus A, this is another set, and whose element small d is defined by those rule method, which is greater than 1.6 and less than equal to 2.5. So note that A minus B is not equal to B minus A. So they are not commutative with each other. The union and the intersection. Okay, the definition of union, I should say, union of two sets, A or B. So sometimes I recall this the probabilistic sum of two sets, A or B. So our new set C is equal to the set A union the set B. I will use the symbol over there, cup symbol over there. So in general, if you have n sets, then the union of n sets will be defined by, if I use subscript for A, then C, our new union of n sets equals to A1 union, A2 union, etc. union AN, which is big union. I start from 1 to n, A subscript I. The definition of intersection of two sets, which is A and B, sometimes I record this probabilistic product of two sets. And you have a new set D, which is A intersection B. I'm going to use the symbol cap over there. Therefore, in general, the set D, if you have n sets, and the intersection of n set will become A1 intersection A2 intersection, etc. intersection AN, which is equal to big intersection I start from 1 to n, A subscript I. Therefore, for example, if you have two mutually exclusive sets, A and B, then A intersection B will become the empty set phi. Okay, complement. The definition of complement over set A, I will use A bar, which is S minus A. I will use difference operator over there. So the universal set S minus A. For example, with this complement concept, there are many there are some relationship between the universal set and the empty set. So the empty set bar is the universal set. The universal set bar is the empty set. So that means complement of a universal set becomes the empty set, and the complement of the empty set will become the universal set. In general, if you have a set A, then set A union complement of A will become the universal set S, and the set A intersection the complement of set A will become the empty set. You have a Venn diagram over there. We have a union and intersection and also complement. So we have an example, integer subsets. uh, A, B, C. So with universal set S, which is the natural number, uh, set A has 4 elements, set B has 7 elements, set C has 6 elements. With a Venn diagram uh, in this the universal set S, we have 3 sets, A, B, and C. So C is overlapping with A and B together, but A and B are mutually exclusive. So the set A intersection B is the empty set. B intersection C, you have 3 elements. C intersection A, you have 2 elements. A union B, you have how many of them? 11 elements. So uh, uh, what is missing? The element 4 in the set C is missing in this A union B, etc. Okay, now we switch to the set algebra. We have a couple of theorems relating to this set algebra. The first one is commutative law, 교환 법칙 in Korean. It says A intersection B is the same as B intersection A. A union B is the same as B union A. So you can switch the order of the operations. And the second one is distributive law, 분배 법칙 in Korean. It says A intersection bracket B union C is the same as bracket A intersection B union bracket A intersection C. Also, A union bracket B intersection C is the same as bracket A union B intersection bracket A union C. So you may think of this intersection as a multiplication operation and union as addition operation. So it's like distributing between those operations, union and intersection. Now, the associative law, 결합 법칙 in Korean. It says bracket A union B union C is the same as A union bracket A B union C, which is the same as A union B union C. So you don't need a bracket whatsoever, actually. Bracket A intersection B intersection C is the same as A intersection bracket B intersection C equals to A intersection B intersection C. So the order of operation is the same when you apply those union operations and intersection operations, because they are homogeneous. They are the same operations inside this associative law. And finally, the De Morgan's law. De Morgan's law says A union B. You have A union B and A intersection B. Now you apply complement. So the complement of A union B is the same as complement of A intersection complement of B. Also, A intersection B, by using this complement of A intersection B is the same as complement of A union complement of B. So you have a duality principle, as we have seen the laws preserved by changing